All right, gang, Math 6610. I'm going to try something a little different here. Instead of writing things out, I think you will agree with me that I don't write really well. So I actually type pretty well. You can read it. Uh, and I don't know. You can shoot me an email and say, hey, Dr. Darber, I like, or Dr. D, Triple D, whatever you call me. You may say, well, I like writing it out better. You may say, well, I like embedding the narrative in the R code, or you might be just like it doesn't really even matter. If it's anything like most things today, we're going to be divided. No, we're not going to agree on anything. So, did I really go there? All right. So anyway, we have our data imported into R. The goals are going to be. I may divide this into two videos. Just not sure. I'm going to try to keep it around 20 minutes. But the goals are just to dive into the descriptives, uh, create the Manova model, look at some post hocs. This example is really cool because it runs into, or we observe a dilemma somewhat, state the hypotheses, and test our assumptions. So again, Manova is an extension to ANOVA with at least two independent variables. There are multiple tests that we conduct. I think as just a standard, let's just go with Peli's trace unless otherwise instructed. And Manova maximizes the calculations between, using the between versus within based on the best linear combination of the dependent variables. Plus it takes some other things into account, namely the correlation between the dependent variables, and gives us more statistical power, as we're actually going to see firsthand in this example. So the assumptions that we want to test is we want to test multivariate normality. We'll want to test univariate normality using Shapiro-Wilk and using Martia's test of multivariate normality. More about that in just a second. We'll want to test homogeneity of the variance-covariance structure using Box-M's test. Want to test multicollinearity. That's really easy. And we want, or we need linearity of the dependent variables within each group. And we'll test outliers as well. If we have mild outliers, I say proceed with them. If we have extreme outliers, you probably want to delete those. Or at least, something I found pretty interesting. I read one time in my life, I got kind of fixated on outliers, and I read a lot on it for about 2 or 3 weeks. I read as much as I could, and what I found is that most outliers aren't really an observed measurement. Most outliers, extreme outliers, let me put it that way, are some sort of clerical issue. You're analyzing ages of high school students, and you end up with this student who's 81 years old. Well, the numbers have been transposed. They should be 18. So I'm not sure that most outliers are truly measurement issues as much as clerical issues. But who knows? They need to be investigated. So the first thing I did is I used the aggregate function. I want to dive in and look at the means and standard deviations for Unit 1 and Unit 2. And let me tell you what's going on here. Let me go all the way to the bottom, and let's just take a look at our data set. What we have is we have a final exam, and there were 20 questions on Unit 1. I'm sorry, there were 10 questions on Unit 1 and 20 questions on Unit 2. So this first student got 5 out of 10 questions correct on Unit 1. They got 14 out of 20 questions correct on number 2. Their IQ is given. That's for a different problem. This is the professor that they had in their class, 3 professors, A, B, and C. And this is the group. Group is just whether they were in an evening class or a day class. Now for this analysis, we only use Unit 1, Unit 2, and the professor. And the multiple dependent variables are the Unit 1 score and the Unit 2 score. All right, so that's important that you know that as we proceed. So the null hypothesis in this problem would be that the mean for Unit 1 is the same as the mean for Unit 2, and the alternative is that the means would be different. Now again, the focus is what I just told you. So the first thing I want to look at is the means. So for Unit 1, it looks like that Professor C's students scored a little better than A and B. Really not much difference between A and C, but there is quite a gap between A and C and B. The standard deviations are relatively close, although there does seem to be less spread in Professor C's class for Unit 1 scores. Unit 2, looks like Professor C's and Professor B's actually scored higher than Professor A. Now, we can't generalize yet. That's just a statement specific to this test. And then it looks, in terms of variance, well, standard deviations, but we can get an indication of variance too. I don't see much difference. So I didn't do this here, but I would probably want to run box plots of Unit 1 over Professor and Unit 2 over Professor, just again to get an indication of center and spread. So the next thing I do is I'm going to run my model, which I do. Remember, I have to mash together the two dependent variables. I'm just running the piecewise trace here. It's the default, and I have no problem. Well, I recommend that you run this one as well, unless instructed otherwise. So we have statistical significance, so we can reject the claim that the means on Unit 1 and Unit 2 are the same. Now we can dive into the effect size. We can see that the effect size is 0.17. So we have an observed large effect. Remember the cutoffs for the partial eta squared are 0.01, 0.06, and 0.14. So we're above 0.14, so we have an observed large effect. Now, the next thing we may want to get into is we want to get into the post hoc. And what I did here is I ran the individual ANOVAs. And so for Unit 1, we have statistical significance at the 0.05 level. For Unit 2, there's no difference across professors. Now, here's the dilemma. The dilemma is we just created a statistical no-no in that we conducted multiple ANOVAs on the same data set. Well, we conducted multiple ANOVAs on two dependent variables, okay? A pair of dependent variables. So what we're going to do here is we're going to inflate the type 1 error rate. Some people say that what we should do is we should adjust the alpha level by the number of groups that we have. Now, okay, so here's, that wasn't very clear. We have two dependent variables here. Some people say that we should take our alpha 0.05, divide by 2, and readjust at 0.025. So we would compare the p-values to 0.025 instead of 0.05. Nah, to me that's a little wishy-washy. But believe it or not, we have to adjust that alpha threshold level some way, because we know that by making multiple comparisons, we're inflating the p-values. Okay, or not inflating, yeah, or inflating the p-value. Yeah, exactly. So what I did next is I came in and did a post hoc. I'm only interested in unit number 1. This is where the craziness happens. I'm only interested in unit number 1 because that's where I achieved statistical significance at the 0.05 level, even though I think testing at the 0.025 level is safer. And you'll notice when I run my Tukey highly significant difference on the post hoc. Now again, I just ran the model in unit 1 because that's all I was worried about at that time. Notice that I don't get statistical significance of any of the pairwise comparisons. Now it may lead you to say, what the, yeah, exactly. Well, what you have to remember is Manova techniques adjust the sum of squares for the correlation between the dependent variables. And what this does, it results in a lot more power, and it allows us to be more likely, have a higher probability of detecting differences. So you might say that the Manova is a much more statistically powerful tool than the individual ANOVAs and certainly the Tukey highly significant difference, even though this is controlling for the family-wise type 1 inflated error rate. So, interesting stuff, and I'm glad it turned out this way because I want this tattooed to your brain that these univariate tests don't always align with the Manova, the multivariate test, the Manova in this case, because the Manova has more statistical power. That'll probably be an exam question. So the next thing I want to do is dive into the post hocs a little more, and I load the library, the mass package, and I conduct what's called a discriminant function analysis. Now, notice when I conduct that there's a switch in the order. We typically, when we would put, like in the ALV command, it's our dependent variable tilde our independent variable. Well, it's reversed here. And when we get our post hocs, we don't get that nice output that we're used to getting where we have p-values that make our decisions really, really easy. The one thing I will tell you, it's a nice way to get the group means that we worked kind of hard earlier to get using the aggregate function. But what we can determine from this is my tunnel vision goes directly to these two lines. So we have two functions, two variates that have emerged. And notice in the first function that my first component and my first discriminant, my second discriminant have different signs. In my second discriminant and my second function, my discriminants have same sign. These things are closely related. So I explain this, or I do my best to explain it here in just a second. And then I get into the proportion of variance that's explained by each of the linear discriminants. So what I tell you here is the results reveal two discriminants. One describes 73.9% of the variance, and the other explains 26.1%. The first function differentiated between Unit 1 and Unit 2 scores, indicated by one being positive, one being negative. The second variant did not differentiate, indicated by the same sign on the linear discriminants. We can dive into it a little more and get a plot of the discriminant function analysis. So to do that, I have to create the using the LDA command. And again, notice we have a switch in the way things that we usually see them. So I want to show this plot, so I'm going to come back up and get it. I got a lot of stuff down here. Let me go back up here and get that plot. All right, where is it? Yeah, right here. Now, what you have to do here is kind of tricky and takes a lot of patience. What you have to do is for LD1, you have to draw a vertical line at 0, and you kind of compare the cases to the left with the cases to the right. And I actually went through and actually tested this, I eyeballed it. And what I noticed, this is where a lot of students just say, Darbo, you've lost me. I want p-values. I don't want all this stuff. Yeah, we all do, but sometimes it doesn't work that way. So what I found here is that when I draw the line at LD1, that vertical line, I notice that it differentiates between Professor A and Professor B. I think I have just about the same count of C's over here as I do over here, but it seemed to differentiate between my A's and my B's. Whereas LD2, if I draw a line right here, it seemed to differentiate between Professor C and Professor A and B. So go through and count those and examine their proportions, and it seems to do a pretty good job of that. You know, again, not as convenient and clean as our p-values that we're used to, but sometimes we have to dive into our plots and actually examine a little further. All right, I have thrown a lot at you in this video. Head may be swimming. I don't know what's going on. Let me go and grab this. I think what I'm going to do now is I am going to end this video and start back with, I think we're, let's see, where are we? Yeah, with examining the assumptions. All right, take care.